Hello, everybody. This is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. Today, we're looking at checker borders and building expressions. This is actually the first lesson in the C 2.0 Algebra 1 curriculum. And to be completely honest with everybody who's viewing these videos, it's a lesson with which many teachers have horror stories, especially from the first year of the implementation of the curriculum. And a lot of those tragic experiences that teachers and some of our students experienced had to do with the fact that it wasn't really clear where the lesson was going. But the lesson actually has a very important place in the overall schema of Algebra 1. And we're going to talk about that as we go through. In Unit 1, Topic 1, the students learn to write and use expressions to communicate observed patterns. The key ideas are that there are patterns that allow various equivalent models for expressions. And algebraic expressions communicate meaning and context. And that last one in particular is where a lot of this video is going to go, and it's where the lesson was originally supposed to go when the curriculum was rolled out. Again, we're going to explore that in a minute. One of the helpful skills that students have learned is that rewriting an expression in different forms can shed light on how quantities are related. And this is done under the 7th grade standards in Math 7 and C 2.0 IM. So the checker border problem. It's the first lesson in the Algebra 1 curriculum, and C 2.0 Algebra 1 begins with this problem-based task in which students are determining expressions to model the number of colored tiles on the border of the diagram. As the lesson progresses, students are asked to generalize and notice patterns as the size of the floor expands. So we're going to talk about some alterations to this. The pool border task the checker border task is actually a redo of an older task called the pool border. And the pool border is this really great, rich, open task. It's great for something like the 5 practices and for an inquiry-based approach. It actually comes from some NCTM materials, and the original version is much simpler, and it can be taken in many different directions depending on the level you're teaching and the needs of the students in front of you. So instead of worrying about the total number of tiles in C 2.0 Algebra 1, what we really want to do is we want to start by asking how they visualize groups of tiles and write expressions to match their visualizations. So instead of using the C 2.0 checker border, for this video, we're going to go back to the original version, the pool border, where we're just looking at the tiles around the blue pool in the center of this square. This task is also available as a Desmos activity, and the Desmos activity is true to the original pool border problem and is excellent as a replacement for the checker border lesson. So now let's talk about some common visuals that students will give us. And these are visuals about how those exterior tiles are grouped. So some students may tell us that those exterior tiles are 4 groups of 4 tiles when we have this 3x3 pool. Some may say that there are 4 groups of 3 tiles and the 4 corner pieces. Some students may see the middle piece and the 4 corners expanding. And so we have the 4 groups of 3 tiles at the corner, and we have the 4 middle pieces. And there are some other variations of this. Some students may see this as 2 groups of 5 tiles and 2 groups of 3 tiles. And last but not least, some students may actually see this as the difference of squares. There's 25 or 5 total tiles or 25 total squares here. And what we're doing is we're subtracting the square from the pool, which is a total of 3 squared or 9. Now, what's important here is that we're going to see a lot of these different representations, and that's really what we want. We don't want one thing because we want to be able to connect the different visualizations together to show why they're all valid and to start to explore some patterns. So these are the two most common ones that students come up with, and we're going to be working a lot with those and some others. The most common ones are going to be the four groups of four and the four side pieces, or four groups of three and the four corners. And this can be used to take the lesson into an area of equivalent expressions and proving the distributive property. So we can rewrite 4 times 4 as equal to 4 times 3 plus 4 times 1. And working backwards to validate the distributive property, we can really rewrite 4 times 4 as 4 times 3 plus 1. That validates that distributive property that we have 4 groups of the 3 and 4 groups of the 1. And so this is a way that we could go back and re-emphasize the distributive property. That's probably not where we want to go because students should already have the distributive property down. And in Algebra 1, we're really interested in the patterns, not the mechanics of the computation. So let's start expanding the pool border and let's start looking at some more expressions. When we expand the pool from a 3 by 3 to a 5 by 5, students may continue the visualization they had in the following ways. The 4 groups is no longer 4 groups of 4, it's now 4 groups of 6. It's no longer 4 groups of 3, it's now 4 groups of 5 and the 4 corner pieces. And that's the same for the middle diagram. And then it may no longer be 2 groups of 5 and 2 groups of 3. It may now be 2 groups of 7 and 2 groups of 5. And for the people who are working with the difference of squares, we may now have 7 squared minus 5 squared. And so in the course of this lesson, we want to keep expanding the diagram, and what we want students to do is to keep with their visualization and keep writing expressions for the visualization that they have chosen. And what this allows us to do is track as a class all of the different versions of expressions and start to notice some patterns. And we can chart that across the different dimensions of squares. So for example, a 3 by 3 and a 4 by 4 and a 5 by 5, so on. If we're looking at version 1, we're going to start to see these patterns emerge, where every time we increase the size of the square, what's in the parentheses is 1 more than whatever the side length of the square was. So that when it was 3 by 3, it was 4 times 4. When it was 4 by 4, it was 4 times 5. 5 by 5, 4 times 6, and so on down to 4 times, any number n, it would be 4 times 1 more than n. And when we start to look at version 2 and 3, something similar happens. When it was a 3 by 3 square, it was 4 times 3 and 4 more. When it was a 4 by 4 square, it was 4 times 4 and 4 more. When it was a 5 by 5 square, it was 4 times 5 and 4 more, so on, so that whatever size square we have, n by n, the expression for the pool border is just 4 times n and 4 more. When we look at version 4, some of the same patterns start to occur. We started with 2 times 5 plus 2 times 3, and we had moved to a 4 by 4, we would see a 2 times 6 plus a 2 times 4. And when we go to a 5 by 5, we saw 2 by 7. 2 times 7 plus 2 times 5. And if we keep going with that, one of the things we'll notice is that within the first set of parentheses, we always have 2 more than whatever the dimension of the square is. And in the second set of parentheses, we always have exactly what the dimension of the square is. And in version 5, we have our difference of squares. And again, here, we always have a square that is 2 more than whatever the dimensions of the pool were. minus a square of the dimensions of the pool. And so the overall intent here is that we're no longer focused on algebraic expressions as a calculation tool, but now we're focused on algebraic expressions as a representation of our visualization and patterns that we've noticed. And so it takes the algebra away from can you calculate this to can you model this, and can you do it succinctly? I hope that this lesson helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.